This is Dr.L.JETHRUTH EMELDA Mary, Assistant Professor in Mathematics, St.Joseph College of Arts and Science, Autonomous, Cuddalore. I am going to take this video lecture for 2nd MSc Mathematics in Graph Theory. Here we are going to discuss about Euler's tour and Hamiltonian cycle. We know that what is Euler tour or Eulerian graph. A graph which contains Euler tour is nothing but Eulerian graph. Here we have a theorem. A non-empty connected graph is Eulerian if and only if it has no vertices of 4 degree. Let us see the proof. We are given as G is a Eulerian graph. It is if and only if statements. We shall prove it in two cases. Assume that G is Eulerian and prove that it has no vertices of 4 degree. So let us take G is an Eulerian graph and C be the Euler tour of G. Because every Eulerian graph admits Euler tour, therefore that Euler tour is taken as a in the form of C. So C is the Euler tour of G with origin and terminus at U. Each time a vertex B occurs in an internal vertex of C, so two of the edges incident with B are accounted for. Since an Euler tour contains every edge of G, therefore degree of V is always even for all B not equal to U. Similarly, C is the Euler tour. It starts and ends at U, therefore degree of U is also even. Hence, G has no vertices of odd degree. So therefore in the case 1 we assume that G is Eulerian and we prove that G has that is every vertex of G has no odd degree. Next we will move to case 2. In case 2 we assume that G has no vertices of odd degree and we must prove that G is Eulerian. So for that the converse part is, suppose G is non-Eulerian graph. We shall prove this theorem in contradiction method by assuming that G is non-Eulerian. So I assume G is non-Eulerian connected graph with at least one edge and no vertices of odd degree. No vertices of odd degree. Therefore, choose just a graph G with a few edges as possible. Since each vertex of G has degree at least 2, therefore G contains a closed trail. G contains a closed trail. So I take it as that to be C. Let C be a closed trail of maximum possible length in G. Therefore by assumption C is not an Euler tour of G. Because it is, I assume it is C is a maximal possible length in G. It is a closed trail of maximum possible length in G. Therefore C cannot be a Euler tour of G, and so G minus E of C, that is edges in C, has some component G dash with number of edges in G dash is greater than 0. Since C is itself is Eulerian, therefore it has no vertices of odd degree. Thus the connected graph G dash also has no vertices of odd degree. And also number of edges in G dash is less than number of edges in G. It follows from choice of G and that G dash and Euler tour C dash. Now because G is connected, there is a vertex B in B of C as well as B of C dash, the vertex set in cycle C and vertex set in C dash, and we may assume that without loss of generality B is the origin and terminus of both the cycles C and C dash. But C and C dash is a closed trail of G. So this is a contradiction to our assumption that G is a non-Eulerian graph. So whenever G has no odd vertices, definitely G must be Euler graph. Hence we prove the theorem. The next is corollary. A connected graph has an Euler trail if and only if it has at most 2 vertices of odd degree. A connected graph has Euler trail if and only if it has at most 2 vertices of odd degree. So what is the difference between previous theorem? Here the graph has no vertices of odd degree. Here we have at most 2 vertices of odd degree. G has at most 2 vertices of odd degree. So this is also if and only if statement. So I just assume we prove this in two cases. Assume that G has Euler trail And then by using the previous theorem we can say that each vertex other than the origin and terminus of this trail has even degree. Hence the first part is proved. For the second part or the converse part, we assume that G is a non-trivial connected graph with at most 2 vertices of odd degree, and we must prove G is Eulerian. Suppose G has no such vertices, then again by theorem 4.1 you can say that G has a closed Euler trail. Otherwise G has exactly 2 vertices u and v of odd degree. In this case G plus E denote a graph obtained from G by addition of new edge E joining u and v. Clearly each vertex of G plus E has even degree, and so G plus E has Euler 2 graphs. That is, the Euler 2 is denoted as C. Hence G has Euler trail of G. Hence the proof. Now we move on to the another topic that is called Hamiltonian cycles. Hamiltonian cycle also we already learned, that is a path that contains every vertex of G is called Hamiltonian path. If a graph admits Hamiltonian cycle, then the graph is said to be Hamiltonian graph. Okay, so it was discovered by the Hamilton in the year 1956. So it is named as Hamiltonian cycle or Hamiltonian graph. A graph is Hamiltonian if it contains Hamiltonian cycle, and we have given some examples for Hamiltonian as well as non-Hamiltonian in the following slide. So this is an example for Hamiltonian graph, and this is an example for non-Hamiltonian graph. The Herschel graph, this is called Herschel graph. So this Herschel graph is non-Hamiltonian graph. Based on this we have a theorem. A graph G is Hamiltonian if for every non-empty proper subset S of V, omega of G minus S less than or equal to modulus of S. This omega of G minus S means the number of component of G minus S is less than or equal to the cardinality of S. So what is S? S is the non-empty proper subset of the vertex set of V. So when I remove the vertices S from the graph G, so we will be getting a graph that is named as G minus S. Then definitely it will be a disconnected graph. So the omega of G minus S, the number of component of G minus S will be less than or equal to the number of vertices in the proper subset S of V. So let us see the proof now. Let C be a Hamiltonian cycle of G. Then for every non-empty proper subset S of V, omega of C minus S less than or equal to mod S. Because I assume that C is a Hamiltonian cycle, when I remove the vertices from the cycle, definitely that C minus S will be a disconnected graph. The number of component will be less than the number of vertices in S. Also C minus S is a spanning subgraph of G minus S. It is also obvious, and therefore we conclude that omega of G minus S is less than or equal to omega of C minus S, which is less than or equal to modulus of S. Okay, thank you students for watching this video.